I'm Matthew Venn, and the course is called Zero to ASIC. And you're Arya. So
Yes.
you're also making an application, or have made an application. It's all very close to the end now, to the Skywater Google Efabless shuttle. And one of the reasons why I was interested to talk to you about it, because I know your project's about an open source FPGA, right?
Yes.
So maybe you could just give us a little bit of information about what your project's about, why you decided to get involved in that.
Okay. Well, our project is actually a class project for a course at UC Berkeley. And sort of the course mandate is pretty broad. We just have to look at VLSI design and come up with a big project that's worth taping out. And it was in both my advisor, who is the professor of this course, John Warshnick, and my research interests to look at FPGAs. And so at the beginning of the semester, we proposed to the entire class of about 15 people that we all build different parts of this FPGA and bring it together into one full fabric using Skywater, which is now entirely open source. It seemed pretty exciting because it was very accessible. And so there's two things. One, like there aren't that many open source FPGA implementations. There's a lot of effort into generatable FPGA fabrics from Verilog, the likes of OpenFPGA and the Princeton reconfigurable array. And they solve a very good problem. I mean, they have a very nice purpose, which is to enable architecture researchers to sort of explore the FPGA design space rapidly. But there's still like a dearth of expertise, and knowledge in building the fabrics themselves. So most students, for example, who go through university will maybe use an FPGA in one course, but they won't know how it's put together. They won't understand fundamentally what the chip is and what it's made of. And so in that way, it's a bit different to all the other projects that have been done recently, which are just like RISC-V cores. I mean, a lot of the other courses we do are RISC-V cores, or like DSPs, AI, ML accelerators of some kind, because it's fashionable. And those were all great, but we thought maybe it's time to look at FPGAs again, because, you know, with the end of Moore's law, everyone keeps talking about it being dead, and the end of Dennard scaling, there's sort of like a renewed interest in accessible accelerators, and we think that they'll probably have a second time in the sun as a result. But to get there, people need to know more about them.
So like have your RISC-V core and then a little bit of FPGA fabric on the side to accelerate whatever the microcontroller is doing at that moment. Okay.
Yeah.
Do you have any pictures of your FPGA fabric that you can screen share?
Oh, yeah. One of them works, I think. I think I have the last carousel. Let's have a look.
I mean, like, we don't need to show GDS, but like the schematic of your logic tile. You do? Is it like?
Yeah, we have the documentation. I can show you the GDS if that's easier.
Yeah, well, both. Yeah.
Okay, so first,
the only logic tiles that I'm really familiar with is the ICE40 ones that have a 4-input mux, a flip-flop, some carry logic, that kind of stuff.
Okay, so we don't, I can show you the documentation. We don't have the sort of polished documentation ready, but we have what every team has done. And I can describe the structure to you. It's a very vanilla FPGA. It's like you read a textbook on an FPGA, this is pretty much the first thing it'll come up with. And that was on purpose. But there are a lot of ways you can do interesting things within it. So here we go, I have this. Okay, so this is just the documentation on the Caravol repo that we have. Okay, so the way we organized the design was bottom up. We got one team to work on the configurable logic blocks, which has the LUTs in it. Another team to work on an SRAM tile, and another team to work on a multiply accumulate unit for faster arithmetic. And so I can just go through this from the bottom up. First of all, well, maybe you want to see the top level first. Yeah, there it is. It sort of looks like, where'd it go? Here, this. Can you see this? Okay, so
yeah,
you have, it's called like island style because you have this like regular repeating pattern of logic blocks, and the switch boxes and connection boxes that connect them all together, and the grid just goes on forever. It's like a big sea of tiles. And so in this sense, it's not very optimized for connectivity, because if you look at like a modern like Xilinx chip, for example, there are these big thick wire full channels between these tiles that run different spans horizontally and vertically, and we kind of do away with that for simplicity. Every tile is basically just connected to its neighbor, and so to get from one tile to a couple over, you have to connect through the neighbor's switch boxes, and so that's slow, but for our purposes it's fine. But yeah, this is basically it. There's the logic blocks, switch boxes, and connection boxes. The memory and the multiply accumulate units have larger versions of these, which are distinct as a result. And otherwise, it's only this many structures that just get repeated.
So a question about the target to ASIC flow then. So did you harden each of these little blocks and then place them?
We tried everything because initially the tools had a lot of problems synthesizing dense cells that were very large. It's not cell, well, dense tiles that had a lot of cells in them, and they're very large. So for example, I started with this multiply accumulate unit, and I could not get the tools to achieve density or even work without splitting everything up into its own little tile and then hardening that individually. But then as time went on, the tools improved a little bit, and we kind of understood how to avoid the constant nagging of like density value too low and blah, blah, blah. And we ended up being able to synthesize, for example, a whole CLB tile out of the CLB block here and the two connection boxes and a switch box into one hardened macro. And so then that became the sort of the final building block.
Okay, and then you were able to duplicate those in a regular pattern.
Yeah, and that's what I'll show you in the next shot. Interestingly,
yeah, that would be great.
Our multiply accumulate unit, when we first built it, is too big, and so it didn't really fit on our.
How many bits wide is the multiply?
It was 32 bits by 32 bits, and then because it's an accumulate, the output size was doubled. Well, it's 4 times that, because you need double the width just to get a product, and then we have 4 times that for like a successive accumulation of those products. And that was huge. That would have been about a quarter of the size of the Caravelle die that we had, like the user space we get. So we were like, okay, maybe that won't fit. So in the interest of like getting this into the deadline, we kind of just dropped it from the submission to tape out. But the plan is, now that we understand things better, to make it much smaller, to make the operands, half the size and the output 25% narrower. And I think with what we know now, we can probably fit that in. Likewise, the SRAM, we were waiting on OpenRAM, the compiler, to be released. And I had to look at some of the pre-release stuff they were doing, but there were always like a few little niggly things that made it not quite ready. And so we had to drop that as well, because we needed, a specific kind of port configuration. For example, a 1-bit wide read-write instead of like the usual 8-bit, because the output could be coming from a 1 LUT, for example. Anyway, long story short, we just had to drop that too. But once OpenRAM is ready, our control logic is ready, and we can put that into. And we think size-wise that will easily fit. So what you're about to see is only these CLB tiles that are hardened as one single block.
Okay, so each one of these big squares is that set of 4 blocks, is it?
Yes. So this is a configurable logic block, which is the LUTs that you mentioned earlier, and some switch boxes. Well, 1 switch box which connects it to its neighbor, and then 2 connection boxes.
Can you zoom in on that for us?
You can't really tell the structure by looking at it, though. There's clearly like a massive, highly interconnected area, which I suspect is the switch box.
Yeah.
And then, so
I suppose I thought I was expecting to see something much more regular because
well, see, this is an interesting thing.
FPGA fabric is so regular.
This is a very interesting thing. And this is actually my personal research direction. I think that synthesizing FPGAs like this is good because it's easy and it makes it accessible. But I think it leaves a lot of performance on the table because at the end of the day, you're just trying to like put these standard cells and arrange them as best as you can. And you're not going to use all the available space. You're going to have too many extra.
Yeah, because I was wondering whether you were going to show me like a new standard cell that was a logic slice, basically.
Oh, that is the plan. That is my personal plan. I have like 3 months to do that now.
Right.
Yeah, no, that is, I mean, it makes a lot of sense, right? And that's what the big FPGA companies will do. I think the biggest blocker has been finding the right tooling to do it with, because you can write your own thing that will write GDS or write a LEF or whatever, and then what happens when you need to port that to a different process? You have to write the whole thing again, or you have to like try and yourself take care of all the different process DRC constraints and so on. So I was thinking of using BAG, but I've been waiting for that to be ready, and it now is. So yeah, no, that's a great idea. I'm going to do it, but we don't have that for you today. I'm sorry. This is what. So for example, OpenFPGA, they have the same idea, but they've gone and added custom cells. They've added like a custom, like a mux or a latch. I think they called it a flip-flop, but it was a latch for storage within the LUTs. And just by adding 2 small custom standard cells, which get rid of like unnecessary buffering, because you know the inputs and outputs, then I think they got like an almost 2x improvement in performance.
In terms of speed or size?
In terms of speed. So, I mean, the whole thing was a lot smaller and the delays were much lower. And it came very close to commercially competitive in the sense like it could compete with like an equivalent commercial chip. So that, I mean, it shows you that it's really promising to take that path and try and do everything sort of half manually, like to write a layout generator. But there are too many.
So it would be a little bit like Open RAM, but for an FPGA.
Yeah, exactly. It would be a compiler like Open RAM. Or maybe actually just a straight generator, because Open RAM will assemble existing SRAM tiles and then put the decode logic in. But I don't know if we'd do it that way.
Okay.
No, so
what are you hoping to learn from this experiment?
I mean, principally the point of the class is to teach our grad students how VLSI design works at a more practical level than all the sort of first, like the low level academic stuff you learn in like one course and then move on. So, you know, like what the power grid does and why you need tap cells and stuff that's pretty basic, but also how do you then go from start to finish? Like they had to build the RTL for these blocks, make the test benches, get the functional simulation, the gate level simulation, the end-to-end simulation with Caravelle, and they had to think about how they trade performance with cost in terms of area, you know, when they're like, for example, deciding on how to do decoding for the SRAMs, because an FPGA SRAM, like a memory tile, should be configurable by the user as, you know, like a 32 by 8 or a 64 by 4 or something. And like, how do you build that? And so it's just a big design exercise. There's nothing really researchy about this or new. I think the most interesting thing is that it's done in this open source flow. And I think being one of the first classes to do it made it difficult, but because the community was so active and engaged, I think it went a lot more smoothly than we thought. And so on what you were saying earlier, you're wanting to make a course. I will spend probably 2 weeks from next week turning what we did into a lab manual so that other persons such as yourself or universities can take it and work with it. But I mean, the audience of that would be probably university students. And I think the emphasis would be on teaching people what the different parts of the tool flow are and how and why they sort of work. Because we have another class. I mean, the class you take prior to this one, you have to build a RISC-V core, but we give the students the entire ASIC tool flow, and we just say, okay, run make, and it'll work. Actually, it uses Berkeley's Hammer project. I don't know if you've heard of it, but the whole point of that is to abstract that problem away and make it so that you have to worry about the digital design and not the ASIC tool flow. But then when you come to this course, you have to learn about what the tool flow actually is and why. Yeah, that makes sense.
A little bit more under the hood.
Yeah, because I mean, you can join a. I mean, the thing is, normally you do like the first course, and you'd go to industry and you get a job doing this, and they would teach you how their tool flow works, and you'd be fine. But for a lot of people, that isn't very satisfying. So we've had a lot of, I think, engaged students more so than normal, because it's really fun to be able to do this and to kind of know why it works.
And do you think actually taping something out gives that like a bit of extra excitement as well?
Oh, absolutely. I mean, we definitely dangled it like a carrot. To be honest, we like, in all realism, we didn't think we'd make it, because everything about this was unknown, and we didn't have that long, and we are in the middle of a global pandemic and so on. So
why make it easy?
Yeah, why make it easy? So we were like, okay, we're going to aim for this, but we don't really like. When we started, we had no idea what the end result would need to look like to fit onto Caravelle. And then I think 4 weeks ago they released the sort of harness and the pre-check tool, and so finally we realized, and so I started just like bashing what we had until it fit. But yeah, I think a lot of the students really engage with that. They really got excited by being able to have a real chip at the end of it, being able to look at it. I mean, I personally would. So I think it's awesome.
And what do you think about like the possibilities for this kind of shuttle program in the future? Because you're like in the academic world.
Yeah, I am. Well, so before I came to grad school, I actually worked as a software engineer, and I think in my experience there, well, I mean, so I worked at Google with actually Tim Ansel, and I think what he's doing is a great example of what will happen when he's successful, right? And this stuff becomes a bit more democratized, and that there's a lot of technically minded people who want, need, or could use sort of these sort of accelerated digital logic devices for whatever purpose they have, and they often avoid it because it's just too hard. It's sort of like this arcane knowledge that is like hard won, and that you have to fight for when you win it. Am I still sharing?
No, I turned it off so that I'd be able to see your face.
Oh, you broke my Zoom, which is normal. It's just another day.
It is normal.
Anyway, what's the question? Do I think? Yeah, no, I think like there are a lot of like tinkerers. Like, okay, at one level there's tinkerers, right? There's hobbyists, enthusiasts who like my younger self would really have loved to just build a chip because they could get it to do something cool. But then at a higher level, like as you go up the sort of experience stack, there are, and I guess the stakes stack, there are companies who have real business needs for sort of accelerated logic, and they can't afford to build a chip, and so they'll usually go.
Well, why not? Why would you? I mean, how would you explain to somebody why they should build a chip instead of using a GPU or an existing FPGA?
So GPUs are exceptionally good at their very specific job, which is massively parallel, basically arithmetic. And that is great. And I think if you can use a GPU, you should, because you're not going to build a chip that does GPU better than GPU, right? Unless you join NVIDIA. So I think as a computer architect, the interesting hole that's left is sort of the classes of stuff that are not trivially acceleratable with, like a vector core and a general purpose computer or a GPU, but that are nonetheless important. And it could mean that, I mean, you could want a chip not just because of performance, right? You might want it to be low power. You might want something that runs on like very little battery for a very long time. and just kind of sits in the corner of your garage, I don't know, or in your warehouse. Or you may want like you may have an algorithm that you can't parallelize, and so you implement it as a circuit to try and eke out performance, and then you would normally put it on an FPGA, and you kind of be wasting FPGA resources, and you'd have this like $200 thing that sits in the corner, plus just for the chip. But now you have the option of, if it's justified, building a special purpose chip for it, which will have lower power and probably better performance.
And we can clearly see that Google are interested in this, given that they're sponsoring.
Yeah, I mean, I don't mean to speak from my experience there, but companies like Google have a lot of need for compute in ways that they need more performance, basically, where they can't just rely on general purpose compute scaling. And like if you think of Facebook and Amazon and Microsoft and Google and all these people with like huge data centers with like very, I think, diverse workloads in some sense, but in others very repetitive. Like there are, like you imagine something that a data center has to do all the time for every application is like handle communication, right? It has to handle network traffic. And that isn't like a static thing, and that changes all the time. And so it's nice to be able to accelerate that somehow, without having to wait for just faster, like Intel or AMD chips. But now I'm just speculating wildly. I think like, I mean, at 130 nanometer, the sort of scope of this is limited to hobbyists, but and like low power applications and like low cost commercial devices. But the exciting thing about OpenLane is that when you have this tool flow, and when you have companies that are willing to invest in this tool flow, then you start to get what happened with Linux in the 90s, where
I think that's where my excitement comes from. Is there's just kind of, it's the unknowable nature of the future once you start putting this in everybody's hands, and the tools have historically been so expensive, and access to actually getting your chip made has been so expensive that we've missed out on perhaps a lot of unexpected, strange experimentation.
Yeah, exactly. And I mean, back to the FPGAs, I think they've kind of fell out of favor for like a few decades because CPUs were going gangbusters, right? They were getting 30, 40, 50% faster a year. And so who cares about FPGAs, basically? No one really did for a long time. I mean, there were always niche applications, but no one was really talking about them beyond that. And now suddenly, because CPUs kind of grow 5 to 10% faster a year, people talk about, oh, how can we accelerate things? And so, okay, the analogy is this, like researchers haven't been able to just get their own FPGAs made or kind of designed to play on unless they had tremendous resources, which kind of locked out most of the research community. Likewise, hobbyists and the open source community haven't been able to tinker with them and innovate in the way that they do. And so the hope is like, if you have like an open source fabric like this, or something that people can just take and use and then improve on iteratively, then you'll start to get those sorts of like refinements that eventually lead to something that is very useful for a lot of people, like Linux.
And we've just seen that with Yosys and IceStorm and the availability of open source. Yeah. So just to bring this back round then, and to finish the conversation, do you have a plan for like a tool chain for synthesis for your custom FPGA? Are you going to use Yosys?
Yeah, we actually do. One of our teams worked on, this one guy, Tan, he's my buddy. We are developing the toolchain to target this fabric in yosys and nextpnr. Awesome. So yosys is the synthesis tool. It uses Berkeley's ABC tool, and nextpnr does place and route. Popular alternative would be VTR from University of Toronto. But for our simple design, we wanted to avoid XML. So that we went with yeah, and then so the idea was, and I mean still is, like we can generate a bit stream for this. We can't really completely map designs yet. I think there are some holes in the process, but currently we generate a bit stream and we like load it manually and we see that things work. But
and you're doing all that in simulation.
Yeah. Yes, but the original plan and the thing we're halfway through doing is being able to, synthesize circuits to the FPGA. The problem was when we first laid this out.
And the last thing you need to do is run yosys and nextpnr on the Pico RB32 inside Caravelle.
Yeah. No, wait. Yeah, no, we're not gonna.
You might not have quite enough RAM. How much do you have? 2K?
Yeah, if that. What was I saying? Yeah, I think that's very interesting stuff, and it it feeds into all of our our research work on the side, which is nice. But yeah, it became just too complicated to try and get OpenLane to work and all the tooling to work at the same time. And that's the thing I was going to say. I remember when I first tried to put this down, I could only fit 12 tiles in because there were power rings in the wrong place and there were halos in the wrong place, and we couldn't get density above 30%. And so with 12 tiles, it's you're not going to map anything. It's kind of stupid. At that point, it was barely worth actually submitting because we weren't going to use it. But after some last minute magic, no pun intended, we managed to get the density right up and squeeze them together. So there's 56 tiles now, which is usable.
Cool.
And so each tile has 4 LUTs, and comparing to your ICE 40 example, these are actually S4.
Okay, so you got 50 tiles and 4 LUTs in each one.
And they're
so you got 200 LUTs in the whole fabric.
Yeah, and they're 4 LUTs. So S44 is this
okay.
So it's 2 4 LUTs stuck together, so it basically can do almost as well as a 6 LUT. So there's 4 of those pairs. Yeah, which is really powerful. So.
Well, thanks so much for your time, Arya. It's been really cool talking to you about your project.
Yeah, no, thanks very much.
I look forward to seeing you actually running a synthesized design on your own FPGA.
Me too.
Or you and your team.
Thanks. Nice to meet you too.
Great. Okay.